Good morning students, I welcome you all for another lecture on the course Computer Architecture and Organization. In the last class we discussed about hardwired control unit. In today's class I am going to discuss about the second type of control unit, which is microprogrammed control unit. Right. In microprogrammed control, the control signals are generated by a program similar to machine language programs. So in case of this microprogrammed control unit, the control signals are generated by a program which is similar to our machine language programs. The meaning of this one is, in case of a previous control unit design, that is in a hardwired control unit, the control signals are generated by a dedicated hardware circuits. But coming to this microprogrammed control unit, the control signals are generated by execution of micro instructions. That means if I divide an instruction into elementary elements, in every instruction the elementary element was a micro operation. To perform a micro operation, we need a micro instructions. So here that's why in the microprogrammed control, the control signals are generated by a program which is a microprogram. It is similar to machine language programs. The second point, the control word CW is a word whose individual bits represents various control signals. Here the control words, it is nothing but a group of bits. Each and every bit that is represents a particular control signals. Each of the control steps in the control sequence of an instruction defines unique combination of ones and zeros in the control word. So what is the meaning of this? In a control steps, in the sequence of controls of an instruction defines a unique combination of ones and zeros in the control word. Right. So consider the following control sequence. In the execution of an instruction add in brackets of R3 comma R1. The meaning of this one is go and add the content of register R1 with the memory location content, the location address is appointed by R3, and the final result was a transfer to again a destination register R1. In order to execute this instruction, these are the sequence of control steps. I have 7 control steps. I already discussed these things in a past lectures. I just took an example for execution of this instruction, how the control signals are generated. For that purpose only, I took again the same example back. So these are the 7 different steps in the execution of this instruction add in brackets of R3 comma R1. So these are the 7 different steps. These are the different control signals that are needed for me to activate different registers as well as ALU and sending of signals to the memory, all these things. Alright. So see here friends, for those 7 different steps, in previous case I have 7 different steps. So here I am assuming that those are 7 micro instructions. So in that micro instruction is nothing but a group of bits. If I see previous case, these are the different signals I would like to generate in the execution of an instruction add in brackets of R3 comma R1. So in order to generate all these things, what I already told you that a control word, it is nothing but a combination of ones and zeros. In that each and every bit represents one control signal. So if I take a step 1, I need a PC out signal, I need a MERN signal, a read signal, select for signal, add signal, and then ZIN signal. These all are needed for me. And if I observing all these things, along with this, I have so many variety of signals I was needed. So each and every signal I was representing with either logic 1 or logic 0. If this PC out signal is needed in a particular micro operation, in that corresponding control word, the bit which is assigned for this C out that must be set to 1. Which is a bit which is equivalent to 0, that means that the corresponding signal is not involved in that micro instruction. So that is the meaning of this. See here friends, those are the 7 control steps. So here if I assuming this a first control step, in the first control step, what are the signals are needed? One is the PCO, second one is MARM, third one is read, and fourth one is a select 4, next fifth one is add, and sixth one is Z. Only these corresponding signal bits in my control word is set to 1 and the rest of the bits are is equal to 0. That I was observing in the next slide. So see here friends, I need a PCO, so it is set to 1, and I need a MARM, so it is set to 1, I need a read, it is set to 1, and again I need a select, that is set to 1, add set to 1, and Z set to 1, and the rest of the things are equivalent to 0 because I need all these signals in the execution of an instruction add in brackets of R3, R1. But out of all those signals, for doing of a first step, these signals must be active. That's why these bits are I set it to 1 and the remaining signals related bits I make it as a 0. Like that for 7 steps. Each step what are the signals I was needed. According to that signals I make my control word. In that control mode the signals which are needed, those corresponding bits are set to 1, and which are not needed for me, those signals I set it as 0. That's you have to remember. Right. A sequence of control words corresponding to the control sequence of a machine instruction constitutes a micro routine for that instruction. What is the meaning of this? See here friends. For example, this is an instruction. This is my instruction. If I split this instruction into partitions, I have different cycles like a fetch cycle, decode cycle, and then execute cycle. Like this, there are different cycles. Again, I split these into a small number of operations. Those I can call as micro operations. This is what I can call is MUO, means micro operations. In order to execute this particular instruction, I have to go and perform number of micro operations internally. What is a micro operation? Micro operation is an elementary operation which is used either to transfer data between two registers, or to do an arithmetic operation, or to do a logical operation. All these things we consider as a micro operations. In order to perform these micro operations, what I need is I need a micro instructions. In order to perform a micro operation, I need a micro instructions. So, in order to execution of this instruction, I have to go and run so many number of micro operations. In order to run this micro operation, I have to go and execute a micro instructions. A set of micro instruction here we can call as a micro routine, or it is also called as a micro program. This is what we can call is a micro program. Micro program means set of micro instructions which are needed for me for execution of an instruction. So that's the meaning of that. Individual control words in this micro routine, that is individual control words, each and every instruction I consider as one control word. Each and every micro instruction I consider as one control word. So individual control words in this micro routine are referred to as micro instructions. That's what I'm saying. And next, the micro routines for all instructions in the instruction set of a computer are stored in a special memory called control store. And some of the textbooks, the same thing is representing as a control memory. The control memory is a place which can hold a number of micro programs. The programs which are needed for me execution of an instruction in a smoother way. So here what I am saying is the micro routines or micro programs for all instructions in the instruction set of a CPU or a computer are stored in a special storage area which is called as a control store, or it is also called as control memory. Alright. Next, the control unit can generate the control signals for any instruction by sequentially reading the control words, nothing but micro instructions of the corresponding micro routine from the control store. That means, in order to execute an instruction in a smoother way, definitely I need a set of control signals. In a microprogrammer based control unit, The control signals are generated by execution of micro instructions. Here micro instruction I can call as a control words. Generally the control words are nothing but micro instructions which are stored in my control memory or a control store. If I want to execute an instruction, I would like to go and took one after another the control words or micro instructions from my control store or a control memory. So that is the meaning of this. So how I can access? So this is the basic organization of my control unit, microprogram. So here it is starting address generator, and sometimes this is we can call as control address register CR, and here I can call as starting address generator. It will generate the address from which location of your control store I am going to read my control word or a micro instruction. So it will generate this address based on instruction register. It gives that information to microprogram counter. So it will take a clock signal as another input. By considering of all these things, I can give a signal to my control store or control memory, and I will get at the output a control word or nothing but a micro instruction, which is helpful for me for generation of different control signals. So here important thing is what is the use of this particular one. If you are thinking that direction, so generation of control signal must be took with a reference to a clock signal. I know this. So that here the clock signal I was given to microprogram counter. It will generate the required timing signals for me. Along with it will generate this starting address generator, generate an address of my micro instruction or a controller, which I am going to read from this control store. So by applying of this information to the input of my control store or a control memory, at output it will produce the control words are nothing but micro instructions. So with the help of these micro instructions, I would like to generate the control signals which are necessary for me to execution of an instruction. Right, that's the meaning of this. Next, to read a control words sequentially from the control store, a microprogram counter MUPC that is needed for me to read a control instructions or a control words or a micro instructions from my control store or a control memory in a sequential order. I took the help of a microprogram counter MUPC. Next, every time a new instruction is loaded into IR, the output of a starting address generator is loaded into MUPC. That means, see here friends, let you can assume this is my control store or a control memory. What is the job of control memory? The control memory or a control store can hold different micro routines or micro programs. For example, this is one micro program. Micro program is nothing but a group of micro instructions. And in this notation here I was using, instead of using micro instruction, I can call here is control word. These are the set of micro instructions or control words which are necessary for execution of one particular instruction. In that case, I am going to execute this micro routine or micro program. So this is a dedicating for one instruction. That instruction is add in brackets of R3, R1 or move R1, R3. In order to execute every instruction, I have this type of routine is exists internal to my control store. And similarly, let you can assume this is another set of micro instructions or control words which are helpful for me to execute some other instruction. So it is also I can call as micro routine or it is a micro program. Like that, my control store or a control memory can hold different routines which are used for me generation of different control signals for execution of the instructions which are exist my instruction set. So this is my control storage or a control memory. Here what I am saying is, if I want to start a new instruction execution, I know that whatever the instruction I was executing by using my CPU, first of all I bring that instruction from the memory, and I can put that instruction in my instruction register. Then I can say that my instruction of fetching operation is finishes. Once a new instruction is concerned to the IR, that is nothing but instruction register, I have to go and start execution of new micro routine. So that's the meaning of this. That new micro routine starting address must be generated by starting address generator. And it is given that one to MUPC, that is nothing but micro program counter. It is loaded with that, then it will generate an address. to our control storage. Later I was getting the corresponding control word from that control storage that will generate a control signals for me. That's a sequence. The microprogram counter is automatically incremented by clock, causing successive micro instructions to be read from the control store. So once I start instruction execution, this starting address information is generated by starting address generator. It will send that information to microprogram counter. So automatically this microprogram counter can be incremented with a reference to clock to go and read next micro instructions or control words I was going to read from my control store, which was contains these micro routines. So that is the meaning of this. So automatically it will be increments. The previous organization cannot handle the situation when the control unit is required to check the status of condition codes or external inputs to choose between alternate courses of action. That means whatever the basic structure I was used, this structure I am not considering condition codes, I am not considering external inputs in the generation of these control signals. Right here I just only consider the clocking information as well as the IR information. Only by considering these are two, I was going to generate my control signal. This is not sufficient for all the cases in the instructions which are present in my instruction set. So that here I clearly mentioned that I have to go and consider the condition code conditions, along with I have to go and consider the external inputs also in the generation of control words. That's what I'm saying. So use a conditional branching instruction. This is the control unit which consider all the conditions. See here friends, I consider external inputs, I consider conditional codes, I consider IR value. These things I was given to the input to do starting and a branch address generator. Previous case it is starting address generator. Now this block name is changes to starting and a branch address generator, because here I was considering conditional codes as well as external inputs. In previous designing I am not considering these things, I was only considering this. But now I was considering condition codes as well as external inputs also. So based on these three informations, this generator circuit sends something to microprogram counter. Then this microprogram counter will send an address to the control store from which location I am going to read my micro instruction or a control word as an output. In the process, every time this microprogram counter can be incremented with reference to clock pulses. That's what already we know that. So this is a circuit, or this is a block diagram which gives clearly the information regarding how my microprogram control unit was organized. So I hope you understand this diagram is. The starting and branch address generator loads a new address into new PC, that is a microprogram counter. Absolutely. In this control unit, the new PC incremented every time a new micro instruction is fetched from microprogram memory, except in the following situations. That means this is my microprogram, or I can call as a micro routine, which may have a set of instructions like this. In order to get the control signals, my control unit, I have to go and read instruction by instruction from this micro routine or a microprogram by using my setup. And here in this case, microprogram counter new PC automatically increments to go and point the next micro instruction in this micro routine or microprogram. That's what I know. But here the sequence can be changes for different cases. That means my new PC is not increment always. Sometimes a new PC value may alter for different cases. What those are different cases that I am going to discuss now. So generally your new PC points these micro instructions one by one in order to execution smoothly this micro routine, in order to generate the control signals which are necessary for execution of my instruction. But in this process, this new PC value is automatically increment with reference to clock pulse. That's what I know up to this. Sometimes this sequence of operation may alter when it was a changes. So for that case, I am going to discuss a different situations. In that, my first situation is when a new instruction is loaded into IR, the new PC is loaded with starting address of microroutine for that instruction. I am already told you that for execution of every instruction internally, a microprogram was executed. By execution of microprogram, I was getting the needed control signals for execution of my instruction. So in that process, in order to get a new value onto new PC, when it was possible is whenever the new instruction was copied onto my instruction register IR, then automatically new PC is loaded with new microroutine starting address. That means in previous case some address is available on my new PC, that may not be increments. Here new PC is loaded with new micro instruction address which is based on the new instruction that was copied onto instruction register IR. So that is the first situation. And the second situation is when a branching instruction is encountered and the branch condition is satisfied, then new PC is loaded with new branch target address. Absolutely. If I identify some branching instruction in my program, if I get a branching instruction, no doubt automatically the new PC address must be changes. Because here if I use a conditional branching and the specified condition, the conditional branching instruction was satisfied, then whatever the destination address that instruction have, I must copy that address onto new PC in order to reach that corresponding destination. So that this is the second situation where I am not increment my new PC value by 1 with reference to clock. And coming to the third one, when an end micro instruction is encountered, the new PC is loaded with an address of a first CW in the microroutine for the instruction fetch cycle. That means whenever if I encounter end cycle or end operation, that indicates that is the end for the corresponding instruction. So at that incident what happens is, again my new PC is loaded with a new control word address which is needed for me to fetch a next instruction from the memory. For these three different situations, my new PC value is not incremented by 1, it can be varies based on what are the situation that was exists in my system itself. So this is the scenario. So in this entire concept, what our main aim is, I just recollect once guys, that is if I want to execute an instruction, this is my instruction. This instruction can be split into number of cycles like a fetch cycle, decode cycle and execute cycle like this. To do again each and every sub cycle, we are doing number of elementary operations. These elementary operations we can call as micro operations like this, mu. In order to perform these micro operations, I need micro instructions. A set of micro instructions called microprogram or micro routine. That's what I'm saying. So here each and every micro instruction in this lecture I can call as control word. So here what I am saying is, for each every instruction execution of my CPU, it will go and do so many number of micro operations. In order to perform those micro operations, I need a micro instruction. That means in every instruction execution, I was going to execute again a smaller program which may consist of a number of micro instructions. This is what I can call is micro routine or micro program. So this is one thing. How I can go and access these things? That's what I was discussed. So here for each and every instruction which was present in my instruction set, it is corresponding micro routine was stored in control store or control memory. For each and every instruction I have a dedicated micro routine or a micro program. I will store this corresponding micro routine or a micro program in my control storage or a control memory. By accessing of an instructions of a micro routine in a sequential fashion, I will go and get the control signals which are needed for me to do that instruction execution. So this is the concept of this micro programmed control unit. But here I would like to mention one more point, friends, that is, in this case, the control signals are not generated by dedicated hardware. Here the control signals are generated by execution of set of micro instructions. If I executed a micro instruction, then only I was getting a control signals. It is somewhat time-taking process. That means the microprogrammed control unit generate the control signals at a slower rate. Because here the control signals are generated by execution of micro instructions. It is one of the major disadvantages of this. At the same time, the advantage is the flexibility for this microprogrammed control unit is more. That means if I would like to add some instruction to existing instruction set, is it possible for me? Just what I have to do is, I have to go and write a micro routine or a micro program for added instructions. And those micro programs I can store onto my control store or a control memory. By doing of this, I can go and add a new instructions to my instruction set. But it is not possible in case of hardwired control unit. So, in case of microprogrammed control unit, the flexibility is more because we can easily add the instruction what we would like to add to our existing instruction set by simply implementing of micro routines or micro programs, by simply storing them into the control storage or control memory. I can do this, but it is not possible in case of a previous control unit, that is hardwired control unit. But the disadvantage of this one is the control signals are generated at a slower rate because the control signals are generated by execution of some micro instruction. By execution of micro instruction, that means it takes certain amount of time, so that the control signals are not generated at a faster rate. So this is the difference between a previous hardwired control unit and this microprogrammed control unit. I hope you understand what microprogrammed control unit was. So thank you for patient listening. In the next class, I would like to discuss about micro instructions as well as micro instruction sequencing. Thank you. Thank you very much once again for patient listening. Have a nice day.